You ever stop and wonder how your phone can listen to a song and, just instantly tell you what it is? Think about it. That song is a smooth, continuous sound wave out in the real world. But your phone, it's a digital machine. It only gets ones and zeros. So today, let's explore this massive disconnect and the absolutely brilliant mathematical bridge that makes our entire digital world work. So this is the big question, right? How in the world do you take something fluid and basically infinite, like the vibration of a guitar string, and translate that into a simple, finite list of numbers that a computer can actually process? The key, it turns out, is figuring out how to break it down into its core frequencies. And this is where the rubber really meets the road. You see, the classic mathematical tools for this kind of thing, they were designed for a perfect theoretical world, a world with continuous variables and infinite streams of data. But computers, they live right here in reality. They need neat, tidy, discrete numbers and finite chunks of information. The two just don't speak the same language.
To try and solve this, mathematicians first turned to this really powerful but, ultimately flawed tool. It was absolutely perfect on paper, but completely impossible for any real computer to actually use.
So, say hello to the discrete time Fourier transform, or the DTFT for short. It's built to analyze a signal that goes on, theoretically, forever. And its output? A perfectly smooth, continuous map of every single frequency in that signal. But you probably already see the problem, right? Those words, infinite length and continuous spectrum. A computer hears that and just says, nope, can't do it. And hey, don't just take my word for it. The source material itself calls these features troublesome because, simply put, they're not numerically computable. You just can't ask a computer to process an infinite list or to store a perfectly smooth, continuous curve. You'd have to just start chopping things off, making guesses, and you'd lose all that precious precision.
Okay, so a totally new approach was needed. Someone had to get clever and figure out how to adapt the beautiful idea of the Fourier transform to work inside the strict, finite world of a computer. Let's dig into how they cracked that code.
The solution, it turns out, came down to two simple, but honestly revolutionary steps. First, instead of trying to look at an endless signal, you just take a small, finite snapshot of it, a limited number of samples. And second, instead of trying to calculate that perfectly smooth frequency spectrum, you just measure or sample that spectrum at a handful of specific, discrete points.
And with just those two changes, a brand new tool was born. This one was designed from the ground up, not for some abstract theoretical perfection, but for cold, hard, computational reality.
And this is the hero of our story, the discrete Fourier transform, or the DFT. It takes a finite list of numbers as its input, and it spits out a finite list of numbers as its output. It's a transform that finally speaks the language of computers. It's practical, it's computable, and it's the engine that drives pretty much all of digital signal processing.
But there's a twist. See, just because something is possible for a computer to do doesn't mean it's efficient. The DFT solved the big theoretical problem, but in practice, it introduced a new one: speed.
I mean, think about it. For things like live audio, streaming music, or recognizing a song in a noisy room, you need answers right now. So the question became, could the DFT actually deliver its results fast enough to be useful in the real world?
Now, this is where the math gets kind of crazy. The number of calculations you have to do for a direct DFT, it just explodes. It grows with the square of the number of samples. So for just a 1-second clip of audio, you might have over 32,000 samples. A direct DFT would need over 1 billion operations to process it. That's just way too slow.
And this is where the final crucial piece of the puzzle just clicks into place: the fast Fourier transform, or FFT. Now, it's really important to get this. The FFT isn't a new kind of transform. It's a collection of incredibly clever algorithms. Think of them as mathematical shortcuts for computing the exact same DFT, but in a tiny fraction of the time.
And the difference is just staggering. Look at this. For that signal with about 4,000 samples, the direct brute force DFT takes almost 17 million operations. The FFT, it gets the exact same job done in around 50,000. That is not just an improvement, that is a total game changer. It's what unlocked the true power of all this for our modern world.
So let's bring this all home. Why does this whole journey, from an impossible theory to a lightning-fast algorithm, actually matter to any of us? Because the DFT, supercharged by the FFT, is the invisible engine running behind so much of our digital lives.
It's what compresses music into MP3s and makes streaming possible. It's behind every JPEG photo you share. It's fundamental to how your Wi-Fi and 5G network works, and it's even used in things like MRI scans to turn raw data into a clear picture of the human body. As the source material just perfectly sums it up, the DFT is the indispensable algorithmic toolkit of our time. It's the critical link that took abstract math and forged it into the efficient, powerful algorithms that build our digital reality.
So the next time you stream a song or send a photo or connect to Wi-Fi, you'll know about this elegant, brilliant solution that lets the continuous world of sound and light be understood by the discrete world of the computer. It really makes you wonder, what part of our digital world isn't built on this amazing foundation?